The last alkyne reaction we will discuss is an alkyne alkylation. This relies on the fact that alkyne protons are more acidic than alkene or alkane protons. Because they are sp hybridized, they're smaller, which means they're going to be more electronegative. Because these carbon atoms are more electronegative, they can hold a negative charge and be more stable than the other carbon atoms of an alkane or an alkene. So to show you the trends of pKa, an alkane's pKa is around 50, which is really high. It's basically not acidic at all. An alkene drops down to 44, which isn't that much better. But an alkyne pKa drops down to about 25, which means we can deprotonate it with a very strong base. As an example here, we can take this terminal alkyne right here with this CH that can be removed. This can be removed with either sodium hydride or butyllithium or sodium amide. These are very strong bases, but they are strong enough to deprotonate even this carbon atom. When this reaction occurs, we will generate an alkynide ion with a negative charge on our carbon. This ion is very basic, so if we added this to water, for example, it would deprotonate water and generate hydroxide and will reprotonate the alkyne, or it can also act as a nucleophile. So if we add this into an alkyl halide, we can actually get an SN2 reaction where the alkynide will attack the R group and kick off the halide, just like in the other SN2 reactions we've seen. This will generate a new carbon-carbon bond right here. This is the first time we've discussed making a new carbon-carbon bond, one of the most challenging tasks an organic chemist can do. Because this is the first time we've done this, we can actually use it to design synthesis of a new molecule. For example, say we take this propyl chloride. We want to convert this from a 3-carbon chain all the way to hexane, 1, 2, 3, 4, 5, 6, to this 6-carbon chain. You should recognize immediately that it would take 2 of these molecules to make 1 of these molecules. So somehow we need to use the chemistry described above to make this happen. Well, let's apply this. If we have an alkyne and Rx, we can put them together with strong base to make a new carbon-carbon bond. So essentially, here's our Rx, we're already starting with that, our propyl chloride. That will be these 3 carbons here, and our alkyne, with a strong base, will add the other 3 carbons here. So the question is, how do we make this alkyne, and then how do we convert this alkyne back to the alkane? The hardest step in a synthesis is figuring out where to make the new carbon-carbon bond. In that case, it's right here. So now we just need to make the components. First, let's focus on making that alkyne. We have our propyl chloride. The methodology that we've talked about before to make an alkyne involves doing an elimination reaction. In this case, potassium terbutoxide will eliminate the chlorine here and generate an alkene. Now we need to do a bromination, which will give us 2 leaving groups, which will allow us to do 2 eliminations and generate 2 pi bonds. Now we've got our alkyne that we talked about at the beginning, right here. We'll call this alkyne A. Next, we will do this reaction that we talked about, where we add our alkyne with a strong base to deprotonate it. This will react in an SN2 fashion with an alkyl halide to generate a new carbon-carbon bond. Here's our new carbon-carbon bond right here. Finally, how do we get rid of this triple bond here? How do you reduce the triple bond? Well, you should know that catalytic hydrogenation will reduce an alkyne to an alkane. So we will just apply the catalytic hydrogenation conditions, hydrogen with palladium on carbon, and now we get our 6-carbon chain. I believe this example illustrates how hard organic chemistry can be. There are a couple things that you need to recognize along the way. First, we needed to count how many carbons we have in the starting material, how many we had in the product. We had to establish where the new carbon-carbon bond would be, right here, and then we had to find a way to get there. Okay, so you need to be very familiar with all the reactions we've discussed. If you don't know that you can alkylate an alkyne, then you don't know that we can do this reaction here. But then to get the alkyne, you have to be familiar with elimination, halogenation, and elimination again. And then finally, to get to the alkane product, you need to be familiar with catalytic hydrogenation. So this synthesis here actually requires you to not only be able to draw the mechanism and to recognize the products for several reactions, but to put them together to get to an end goal.